All right, great. So yeah, we'll take you through our presentation. We were thinking that it might be good to do the Q&A session after the presentation, but if there are questions that come up that we see as we're presenting, we'll try our best to answer them. Cool. So hi everyone. Yeah, I'm Daniel, and today I'm going to be taking you with Andrea along in discussing our paper AlphaDev, or specifically faster sorting algorithms discovered using deep reinforcement learning that appeared in Nature a couple of, well, I guess it's just over a month and a half ago. And today we're going to take you through the following outline. So we'll start by motivating why we started working on this project, and also why we chose to optimize the algorithms we chose. We'll talk a bit about the assembly game, so the reinforcement learning problem that we formulated, some key aspects of our agent AlphaDev. We'll then dive into the sorting results that we got, and then we'll talk about the hashing, motivation, analysis and results, as well as then conclude with some additional information. So Moore's law is coming to an end, and chips are starting to approach their fundamental physical limits. And as a result, we need to find or try and find new and innovative ways in order to optimize the computing stack. And one such way is to optimize the software that runs on it. Now, there are many optimizations that we think are both non-trivial and or unintuitive that might be difficult to spot. And this is a place where we feel that AI can be particularly beneficial. So when we started this project, we asked ourselves the question, what if we could automatically optimize the world's code using reinforcement learning, and potentially discovering entirely new algorithms along the way that can benefit both researchers and practitioners in both designing and implementing and researching new algorithms. But the question is, where do we start? And we decided to start at the CPU instruction level, specifically optimizing in assembly. So on the left-hand side here is a function that's been written in C++ called variable sort2 that sorts up to 2 elements. The idea is that the compiler then compiles this into lower level assembly, and the equivalent assembly program can be seen on the right-hand side. Assembly is typically executed line by line. An example of an assembly instruction is this move instruction, which is moving a value from register EAX to register EDX. And the general idea of assembly programs is they manipulate values between memory and registers and then yield the same output as the equivalent C++ program. And the reason we chose to optimize in assembly is because we have a lot more flexibility here, and we can potentially discover these unintuitive optimizations that exist by looking in assembly space as opposed to trying to find them in C++, where it might be much more difficult to spot. And we wanted to start by optimizing an algorithm that was really fundamental to society, that is something that's used every day, that's used trillions of times every day across many different types of applications. And sorting algorithms is where we wanted to start. And sorting dates back to thousands of years ago, when in the great library of Alexandria, Zenodotus was sorting the books in the library. It then moved to the late 19th century, where tabulation machines were used for voting and sorting ballots. Sorting in modern day is used in applications such as information retrieval, job scheduling, information display, recommendation systems, and string processing. And it's really used ubiquitously around the world. In addition, it's a fundamental algorithmic challenge in computer science. As I mentioned, we estimate that these functions are used trillions of times every day. And if we were able to improve the speed of these functions, then we would hopefully get these into C++ libraries, for example. This is something that could benefit millions of programmers and applications, and potentially billions of users too. So in order to do this, we wanted to formulate this assembly setup as an RL problem. And for those of you that are not familiar with RL, I'll just give a quick introduction to it. So RL typically consists of an agent interacting in an environment. So if you look on the right-hand side, this is sort of an example that we often use. You have a Mars rover, which is the agent, who's moving on an environment, which is Mars. And the goal here is for the agent to get to the silo in the distance as quickly as possible. Now, typically what happens in a reinforcement learning process is you have a state space, which is the set of possible states. In this case, the state space is the XY location of the Mars rover. There's an action space, which is the set of valid actions. In this case, it could be to move in any of the possible directions. And there's a reward of penalizing or rewarding the agent. In this case, you could define a reward as being larger as it gets closer to the silo, or a negative reward so it gets to the silo as quickly as possible. And the way this works is the agent starts in a particular state, in this case ST, if we look back to the diagram, which would be a particular XY location. The agent then takes an action, which is to move in a given direction. It transitions in the environment to a new state, ST+1, which is the new XY location, and receives a reward for doing so. And the goal is for the agent to learn a policy, which is a function that, given the state of the world, so its XY location, chooses an action for it to take such that it maximizes the rewards that it gets. So now, how did we translate this to learning sorting algorithms in assembly? So we defined what we called the assembly game, where here the state space is the algorithm that the agent has generated thus far, because in the setup, the agent or the player, AlphaDev, is building these functions from scratch. It starts from an empty buffer and it has to gradually build up these functions until it generates, for example, a sorting algorithm. So it's important that it has an understanding of what it has generated so far, even if it's a partial algorithm. And in addition to this, the state includes the state of the CPU's memory and registers, so that the agent can understand while building the program how this affects the dynamics of the memory and registers. The action space here are a set of valid assembly instructions that the agent can select. And the reward is a combination of correctness, so the algorithm that it designs being correct, as well as the speed of the algorithm or its latency. And the way this game works is the agent AlphaDev receives the state of the system. It then chooses an action. In this case, it's chosen a move instruction of moving the value in register 0 to memory location 1. And it adds this to the algorithm that is generated thus far. We then reward the agent by looking at its correctness. And to do this, for example, in the case of sorting 3 elements for a sort 3 algorithm, as we call it, all test input sequences of 3 elements are fed in to the algorithm to generate an output. That output is then compared, in the case of sorting, to an expected output, which is that the numbers should be sorted once it's output by the algorithm. And we then reward the agent based on how well its outputs match the expected outputs. So if it doesn't match a particular output, it's penalized. If it does, it's rewarded. Once the agent learns how to build a correct program, the agent then begins to optimize for latency. When optimizing for latency, there are different ways you can do this. So in programs or algorithms where there's a correlation between the length of the program and the latency, you can use proxies for latency like program length. And this is typically in programs or algorithms where you don't have branching. So you don't have if-else statements, and it's just a single body of code that's being executed line by line. However, in the case where you have branching, so you have if-else statements in your algorithm that the agent is trying to build, the correlations begin to break down very quickly. And in these cases, it's really critical to optimize for actual measured latency. But how do you optimize for actual measured latency? This is an incredibly hard problem. And this was one of the key aspects of the work that we did. And I think one of the important contributions of the work. So latency is something that's very difficult to measure. There's many sources of noise. You can imagine if you're trying to measure the latency of a program and another process interrupts that measurement, you can get a spike in the latency and your measurement just doesn't make sense. In addition to this, we were trying to measure the latency of fairly short programs, and these programs had runtimes in the order of nanoseconds. So not only did we need to have something that could measure, could be as noise-free as possible, it also had to be able to measure on the order of nanoseconds. So we needed a service that was as noise-free as possible to accurately measure the latency. And so what we did is we built something called the latency benchmarking server. And this is a set of separate machines that were separate from the main training of AlphaDev. And every time an algorithm's latency needed to be measured, the agent would process for this algorithm 1,000 measurements across these machines, where each measurement would process 10,000 random inputs. We would then take these random input latencies that are generated, and we would then take the 5th percentile of these measured latencies. And this is something that allowed us to remove a lot of the noise. And these latencies would be measured by measuring the time taken using the CPU performance counter, CPU clock, unhalted core. And by doing all of this, to get a single latency measurement for a given program, we were able to measure changes in latency on the order of nanoseconds. And this is something that was incredibly important for us to do, because this enabled the agent to optimize for latency. So how hard is this assembly game to solve or to win? Well, AlphaDev needs to be able to consider the combinatorial space of assembly instructions when building these algorithms. This is because AlphaDev is building these algorithms entirely from scratch. So it starts with an empty buffer, and then it gradually has to add assembly instructions into the buffer to build an algorithm. And when we look at the possible combinations, we see that it's similar in size to the number of atoms in the universe, the number of games in chess, and the number of possible games in Go. And what makes matters worse is that a single incorrect instruction can invalidate the entire algorithm. So in order to be able to efficiently navigate this space, we needed to add some key aspects to AlphaDev. So AlphaDev is an extension of the AlphaZero agent, which means it already had the ability to perform search through its Monte Carlo tree search. But there were two key aspects that we needed to add on top of that in order to make this useful and able to search this massive space of possible assembly algorithms. The first was the representation. And here we devised what we called the assembly transformer. And you can see in figure A on the right, the idea is that we created a transformer encoder that received as input the program instructions or the algorithm that's been generated thus far, and transforms this into an algorithm embedding. In parallel, we take the state of memory and registers and transform that through what we call a CPU state encoder, which is effectively a multi-layer perceptron that we used in order to generate memory and register embeddings. This was then concatenated together in order to generate the state representation. This state representation allowed AlphaDev to understand the relationship between the program or the algorithm it was building and how that affected the dynamics of memory and registers. In addition, we had to devise what we called the assembly latency value function. And let me jump into those details now. So the assembly latency value function, because it's very expensive to evaluate the latency of a program such that it's very accurate and noise-free, as I mentioned with our latency benchmarking server. We can't do this every time we run Monte Carlo tree search, and we'd have to then run it, thousands or tens of thousands of times, for example. And so we needed a way to be able to accurately predict latency. And so we trained what we called the latency value function, which is given an algorithm that is generated thus far, it could even be a partial algorithm, this latency value function would estimate the future latency of that algorithm. And the way that this worked is that in parallel, whilst AlphaDev was training, there would be many actors, in other words, copies of AlphaDev, that would be generating assembly programs or assembly algorithms. And for each of these algorithms that were generated, we would be using the latency benchmarking server to compute the actual measured latency each time. Now, even though that sounds like a lot of algorithms being generated and latency being computed, when we take into account the Monte Carlo tree search, where we don't need to actually do that, and we're using the latency value function as a predictor there, we only need to calculate the actual measured latency on approximately 0.002% of generated programs or algorithms by AlphaDev. These measured latency values from the actors are used to train our latency value function head. And then during Monte Carlo tree search, at the various nodes where we need to predict latency, or where we would need to compute latency, we're able to predict latency, which makes learning much more efficient and really fast. So the question became, well, what sorting algorithms do we focus on? And when we looked at the C++ standard sorting library, we noticed something interesting. When you call a large sort, for example, sort 1,000 elements where n equals 1,000, what tends to happen is merge sort gets called, for example, and this then progressively breaks down the size of the sort into 2 batches of 500, then 4 batches of 250 elements, etc., all the way down to the point where it calls these fundamental sorting routines of sort 3, sort 4, and sort 5, where sort 3, sort 4, and sort 5 correspond to sorting 3 elements, 4 elements, and 5 elements, respectively. Now, what we then realized is that if we could speed up these fundamental sorting functions, then we could hopefully speed up sort n, in the sense that all sorting functions above that are calling these fundamental routines. And so if we improve the speed of these fundamental routines, we improve the speed of the larger sorting functions. So this was one type of function that we tried to optimize for, and this or generate from scratch, and this we call fixed sort. The second type of function is called variable sorting functions. So var sort 5, for example, is where it sorts elements up to length 5. So it can sort a vector of 3 elements, 4 elements, 5 elements, etc. And here there is branching, because if the length is 3 elements, then do something. If the length is 4 elements, then do something, etc. This was another big challenge for AlphaDev, because it needed to be able to firstly generate sub-functions within the function itself, because these are the branches. And it was critical here to optimize for actual measured latency, because the correlations, as I mentioned, between length and latency break down. So with the fixed sort algorithms, the state of the art are sorting networks. And the reason that these networks are state of the art is because they generate what's called conditional branchless assembly code. In other words, there's no branching, there's no if-else statements. And in addition, these can be parallelized and run very efficiently. So for those of you that aren't familiar with sorting networks, figure A here is a sorting network of sorting 4 numbers. The horizontal lines here are called wires, and the vertical lines are called comparators. And if you look at figure B, here's an example of how a sorting network works. So on the left-hand side, you have 2, 3, 1, and 4 that's fed into each wire in the sorting network. And then when they get to the first comparator, for example, 2 and 1, the comparator compares the 2 numbers and then places the smaller number at the top and the larger number at the bottom. And if you feed these numbers through a sorting network, ultimately then it sorts all of the values. And this, as I mentioned, can be implemented in conditional branchless assembly code. So we thought, let's start by analyzing sort 3. And really, we didn't expect to get any gains out of it. We looked at the assembly equivalent representation of a sort 3 sorting network, which is 18 instructions long. And we thought, let's try and run our AlphaDev agent in assembly game to generate a sort 3 function from scratch and use this as a baseline, for example. And we did this, and to our surprise, it discovered a 17 instruction sort 3 program from scratch. And this was really surprising for us. We initially thought, as you usually do, like this is a bug, there's something wrong. But upon analyzing the algorithm that it generated from scratch, we noticed that this actually did find something faster. And if we look at the original sort 3 sorting network on the left and compare it to the AlphaDev sorting network on the right, we see that this instruction, this move from one register to another instruction was not actually needed and was removed. But we wondered whether there was something more general to this. And we realized that it actually discovered what we called the AlphaDev swap move. Now, what is the AlphaDev swap move? So imagine that in figure A here, you have 3 wires. So you have this type of structure in a sorting network. And by the way, this could be in a sort 3 sorting network, but this could also be in larger sorting networks too, this type of structure. And you have 3 wires, A, B, and C. Now, the idea is that if you have the structure where there's a comparator between wires B and C, for example, then you can assume after that comparator that whatever values are in B and C are already sorted. So let's look at an example on the right. So if we have 2, 3, and 1, when 3 is on wire B, 1 is on wire C, when they go through that comparator, we know that the numbers on wires B and C are sorted. And then if you have comparators that follow this structure going forward, oh, sorry, if you have a keen interest in speaking. Oh, sorry, yeah. So if you then have the structure going forward, these two types of comparators here, then what you're able to do is actually save an instruction by applying this AlphaDev swap move. Now, this is something that I think people found a bit confusing in the paper, but just to fully clarify, in figure B here is the remainder of the sort3 program after you've already passed this first comparator. So after you've assumed that B is less than or equal to C, this part of the sorting algorithm represents the last two comparators. So this is very much a partial sorting function here, but this was put in place in order to highlight the AlphaDev swap move. And you see here, so you can see in memory here, you have 2, 1, and 3. So in other words, wire B and wire C are sorted. And you can see in figure C that this is the same second part of the sorting program after this first comparator of B less than or equal to C. And you can see that the move instruction, move SP, is removed. So every time you have the structure, you can apply the AlphaDev swap move and save an instruction each time. And so when AlphaDev was generating the sort3 function from scratch, it discovered this move as a result. And yeah, so then we said, okay, well, we managed to find something faster for sort3. Maybe there's something that we can improve on for sort4 and sort5. And for sort4, when learning from scratch, it managed to relearn the state of the art. And so we think this might be the sort of globally optimal algorithm that can be discovered. And for sort5, it managed to discover a 42-length sort5 program from scratch. The human benchmark, or the sorting network, is a 46-length program, so it was able to reduce it by 4 instructions. The algorithm that we ended up using for sort5 was actually a 43-instruction program that it learned from scratch, where it learned to apply the AlphaDev swap move 3 times, each circled by these 3 red circles here. And as you can see, the structures look slightly different, but they all ultimately end up with the same assumption that B is less than or equal to C, and the structure of these wires allow you to then apply that move again. When we were working with sort8, which Andrea will talk about a bit later in the talk, we also found that when AlphaDev was generating this algorithm, it discovered what's called the AlphaDev copy move. And again, imagine that you have a structure where you have 4 wires, A, B, C, and D. And if the assumption holds that wire D is greater than or equal to the minimum between wires A and wires C, and you have this structure that follows on the left of a sorting network, then you can apply the AlphaDev copy move, which is what's shown in figure E, which is basically, again, the remainder of the program for this given structure. And sorry, the original is in figure E, and F is where you apply the AlphaDev copy move and you save an instruction, in this case, the move PT each time. So it was really interesting to see that it was, while generating these algorithms from scratch, it was able to discover these quite general moves as a result. So we then thought, let's take our sort3, sort4, and sort5 programs, reverse engineer them to C++, and let's just submit them to the C++ sorting library. You know, we wanted to sort of understand, you know, whether these algorithms, you know, how they needed to be modified further, you know, what the problems were, because we didn't expect these algorithms to actually get into the library, because we really didn't know what to expect from the reviewers of the library. And after a 3-month process where, you know, we wrote many different unit tests, we really kind of narrowed down you know, we sort of really like spoke through the different algorithms. They were actually officially integrated into the library. This was really exciting, which means like right now, this is being used by anyone using the C++ sorting library around the world. It was the first change to these subroutines in over a decade. And the improvements of these algorithms over the ones that existed in the library ranged from 70% for sort 5 to approximately 2% for sort of 250,000 elements in length. And what's really nice about this is it validated our hypothesis that if we improve the speed of these fundamental sorting functions, we should be able to then improve the speed of much higher sorts as well. And it's also the first time that code that has been automatically generated by RL has been incorporated into this library. So we estimate that our routines today are being used trillions of times every day by many different companies, developers, users around the world. Some of the user base can be found at this link, and this includes many different international companies, for example. And we then thought, okay, let's go to variable sort and let's see what we can discover there. And for variable sort, we worked with 3 different functions: variable sort 3, so sort up to 3 elements, variable sort 4, and variable sort 5. And what we found is that initially we said, let's just optimize for length, even though the correlations break down. And what we found is when optimizing for length, AlphaDev was able to find algorithms that were, for example, in the case of var sort 4, 29 instructions shorter than the human benchmark. We then said, let's optimize for latency directly using our latency benchmarking server. And we found, again, that we were able to significantly improve the latency over the human benchmarks in each case. So one of the questions, so just to give you an idea of the types of algorithms that it was building in this case. So this is our fastest variable sort 4 algorithm generated by AlphaDev from scratch. So really it starts from an empty buffer. And what it needs to do is, as it's building this program line by line, it's maybe a bit hard to see in the slide, but if you look at line 417, there's a jump. So it needs to basically branch at that point. And then it jumps all the way down to line 451. And so basically, as it's building the program, it needs to understand where to place the jump, in other words, where it should branch, and it needs to understand where to place the subroutine. So this is actually a very complicated function for AlphaDev to generate, and we were really happy to see that it was capable of doing so. We also wanted to analyze the fastest var sort 4 algorithm that AlphaDev discovered. And if we look at the human benchmark, if, for example, a vector of 4 elements is fed in to the human benchmark, if it's 4 numbers, then it calls the sort 4 sorting network and ends. If it's 3 numbers, it calls the sort 3 sorting network and ends, etc. AlphaDev discovered an algorithm with a fundamentally different structure, in that if you input a vector of 4 elements, it first looks and says, well, is this vector 2 elements in length? Well, it's not in this case. If it was, it would just call sort 2 and end. Then it says, well, if the number of elements are greater than 2, let's sort the first 3 numbers. And again, if it was 3 elements in length, you would be done. But because it's 4 elements in length, it would then have a much more simplified routine that would allow it to just have to sort 2 numbers in this case, because it had already sorted 3 of the 4 numbers. And it's this type of structure that allowed it to have a really significant latency savings as a result. So now I'm going to pass over to Andrea. I saw there was a quick question. Let's see if I can quickly answer it. Otherwise, we'll definitely get to it afterwards. Right, so what we would do in order to determine when to stop generating the code is that the algorithm would either run until a maximum length that we chose, or it would continue running until it generated an algorithm that was correct. And then it knows that it generated a correct algorithm and it could start optimizing for latency. So these were the 2 settings. Cool, so I'll pass it over now to Andrea. Maybe we can swap seats as a result. Yeah.
Cool. So let's just take a step back. So Dan introduced the assembly game, which is how we formalize the problem of program optimization as a reinforcement learning problem. It introduced AlphaDev, which is our agent, the architecture of the agent. And then we started looking at sorting and variable sort and some analysis. In this second part of the talk, what we will do is we will look at some comparisons with other baselines in the sorting environment. Then we will look how AlphaDev can generalize to other domains other than sorting. And finally, we will look at some of the limitations and next steps and where we can go from here. So in terms of baselines, what we did is we re-implemented a state-of-the-art approach called Stoch, which is a stochastic search approach, in the same setting as AlphaDev, and we call it AlphaDev S. What do we mean by same settings? We use the same assembly game, the same correctness checking routines, and we do a like-by-like in terms of resources and work block time. The main difference between AlphaDev and AlphaDev S is the latency value function, which, as Dan talked about, is one of the main components, and is what allows us to optimize end-to-end for latency. We did try using optimizing directly for latency with AlphaDev S, but that wasn't really possible. It was too slow. So the mitigation that we did here is we optimize for program length first, and then we take the top K programs. So those are about like thousands of programs, and we benchmark each one of them, and we pick the fastest among those. So that's how we get around optimizing for latency in AlphaDev S. So how do the two compare? Well, what we observed is AlphaDev outperforms AlphaDev S when learning from scratch. So what do we mean by learning from scratch? It means that we start from an empty buffer and both agents come up instruction by instruction until the final sorting program. So in this setting, AlphaDev S does better than AlphaDev S. However, like in a slightly different setting, which we call warm started. So this is a setting where we start from an already working program, a program that already sorts, and we ask AlphaDev S to optimize this. So to replace instructions, delete or change them in order to find a faster one. Here, AlphaDev S does quite well in terms, and is quite computationally efficient, more than AlphaDev. And the third observation that we did is as the algorithm size increases, AlphaDev explores significantly fewer algorithms than AlphaDev S. So for instance, if you look at variable sort tree, AlphaDev S in the cold starting setting, so when we start from an empty buffer, explores 31 trillion programs. That is a lot more than the 12 million that AlphaDev explores. So we had an intuition, which is AlphaDev better explores the algorithm space. So it has to see fewer algorithms in order to find an efficient one that sorts and one that sorts fast. So we tried to visualize this hypothesis. And what we did is we visualized using t-SNE. So on the graph on the left, you see the three agents, AlphaDev S warm started, and AlphaDev S cold started. And by the way, AlphaDev is always cold started. AlphaDev always starts from an empty buffer. So something interesting that we can see for AlphaDev S warm started is that the type of search it performs is very uniform. So it looks almost like a circle. It does a little bit of almost as a breadth first search, where you start from a solution and then you explore locally in the space. Well, when we compare this with AlphaDev, the search is a lot more interesting, right? Because it seems to move very differently in this space. And if we break down this by correctness, we observe how AlphaDev S cold started for, I think this is for variable sort 4, it's not able to find a correct program. So you start from an empty buffer here, which is incorrect, of course, and then it remains in this space. While AlphaDev starts from this incorrect space, but little by little, you start finding like programs that sort maybe like some permutations, and then incentivized by the reward, then finds program that sorts, and then finally program that sorts really fast. So this is how we compare AlphaDev with baselines, but now a question comes up is that, okay, can we do more than up to sort 5? Can we go to larger sorts? So one main challenge here is scalability. And there are two problems here. One is learning, of course, like the longer is the program, the harder it is for the agent to understand it. And the second challenge is the correctness check. Like as we increase the size of our sort, the number of permutations that we need to check in order to be confident that the algorithm is correct increases very fast. So in order to scale up to sort 8, we have 3 main components. So the assembly graph nets, which I'm going to talk next, the assembly 0-1 principle, which addresses exactly this problem of the correctness check, And finally, using mu0 instead of alpha0. So for those of you who are familiar with mu0 and alpha0, the main difference is that mu0, when it performs the Monte Carlo tree search, it does so in a latent space. So what that means is that when we check for correctness and latency, we don't actually run the correctness check. Instead, we have a learned model. So this is something we were already doing for the latency value function. Now we also do it for the correctness. And by the way, this is a fairly preliminary result. So like we think we can still improve on this. But looking more closely at the first two components, so what's the assembly graph nets? The assembly graph nets is a way to model these programs, adding a little bit of prior information. So for instance, if you look at the example program below, where we have in the first instruction move from memory 1 to register 1, what we can do is to represent these instructions as a graph, where memory and register locations are nodes in the graph, and instructions will be an edge of the graph. So as you can see, we will have like a node 1 for the first memory location, a register 1, and then an edge that connects the two. So creating this structure prior to learning adds quite a bit of information and makes learning a little bit faster, which is nice, of course. Then the second key component is to try to address the problem of scalability in terms of correctness. So I mentioned how like as we see it, like on the left column, we see like the number n is the size of the sort, and we notice that if we want to sort 8 elements, we would have to check more than 500 permutations. It follows what we call a bell order permutations. So, for instance, here it's slightly different than exponential in the sense that, for instance, if you have 2 permutations, we would check 1, 2, 2, 1, and 1, 1. We don't have to check 2, 2, of course, because it's equivalent to 1, 1. Instead, like it would be a lot nicer if we would have just to check 2 to the n, right? Like because for the same size, it has 255 elements. So this would be to just check permutations of 0 and 1. And there is a nice principle in a sorting network, which says that if a sorting network sorts all the binary sequences, so all sequences of 0 and 1s, then it guarantees that it can also sort all sequences of arbitrary numbers correctly. This is a very nice principle because it means that, okay, for sort 8, we only have to check 255 elements. The problem is that it doesn't apply to us. This works only for sorting networks where your only operation is a compare swap, the structures that Dan highlighted before. Our structure is a little bit different, which we call it assembly sorting network. The difference here is that we also have just move instructions, compare instructions, conditional moves, and so on. So what we did is to extend this 0-1 principle to the assembly sorting network. And we were able to prove this principle if a condition is respected. So what we were able to show, and we have the full proof in the paper, is that if we can guarantee that every conditional move operation is applied to values that fall within the range of the previous compare operation, then the 0-1 principle applies to assembly sorting network. So what that means is that, as you can see in the red box, if we have the first operation that we have is a compare operation, and then later we have 2 conditional move less. And then this conditional move less needs to be applied to the same wires that the compare operation was applied to. If that is not respected, so like if they apply to a different wire, then the 0-1 principle doesn't apply. So why is this a good news for us? Is that the good news is that this condition is not too restrictive. So if we enforce this condition, then we have a much easier job because we just need to check the permutations of 0 and 1s. So this is what really allows us to scale up to sort 8. Then, of course, like this doesn't scale much farther because 2 to the n scales quite fast as well, like grows quite rapidly as well. But it's something that can reduce a little bit the problem. So how do we do in sort 6, sort 7, and 8? Well, we tried on sort 6, and then we were able to discover 57 instructions programs. This is 3 less than the human benchmark. Then on sort 7, we save 2 instructions. And finally, on sort 8, we save 1 instruction compared to the baseline. So we are happy to see that we are able to scale a little bit farther sort 5. But the question that we were really interested in is, can we demonstrate that AlphaDev generalized to domain other than sorting? And if there is one algorithm that is probably as famous as sorting, it has to be hashing. Hashing is an algorithm that has been around for more than 70 years. It was invented by Hans-Peter Lohn in the 50s. The initial idea was to bucketize information to speed up search. And now it's used pretty much everywhere, from information retrieval. And of course, it's part of it's a key component of data structures like hash maps. And as you probably are aware, hash maps are pretty much in they're ubiquitous in every coding application. So we started with this ambitious goal and saying can AlphaDev optimize a hashing function? And because if we manage to do so, then we will impact every coding application that relies on hash maps. And we specifically targeted the upscaled library with a flat hash map, which is a famous C++ open source library. So how can we generalize the assembly game for hashing? Well, there are not many changes we need to do. The main one is the definition of correctness. In the case of sorting, it's very clear, right? You want an algorithm that takes an input, always outputs a sorted output. So that's how we would define correctness. It's a very clear definition. For hashing, you don't have a definition of correctness, right? Because usually you have an input distribution, you run your hashing function and you assign some buckets. If you have a function that always returns 0, that is still a hashing function, right? It would basically assign all the items to the same bucket. It's not a good hashing function though. So instead of correctness, what we really wanted to measure is a measure of quality. So given an input distribution, how many collisions are going to be there if you run our hashing function? So this is exactly what we do. So we start this program. We basically decide an arbitrary input distribution, which I'm going to talk in a second, but basically we decide which strings to run the algorithms on, and then we measure the hashing collision, and that's our reward. For the latency, nothing changes. The benchmarking server that Dan talked about remains exactly the same. That is completely generic, right? We take our hashing function, we execute on random input and measure how fast it is. The second change that we did is extend a little bit the instruction set, the assembly instruction set. So we added operations like rotations and the pitch shifts that are not very useful for sorting, but they're quite important for hashing. So when we run AlphaDev on the hashing function of flat hash maps, we were very happy to see how it discovered a different and faster version to hash strings from 8 to 16 bytes. So on the left, what we see, which was the previous version, we would call this function mix twice, and this will perform 2 multiplications. While if you look at the algorithm on the right, it performs a single multiplication, and instead of a second multiplication, it does a rotation, which is this line here that goes a rotation on the low bits and rotates it by 53. And what's interesting is the constant, because we didn't decide this constant. We allowed the AlphaDev to sweep through all different numbers. And something interesting is that it always kind of was coming up either with 53 or 11, which are kind of the complement, right, of 64. And it seems this value to be really good at mixing the low and high bits. We don't have a theoretical answer why it's actually really good. So we have a little bit of intuition, but it's something that the AlphaDev agent was able to discover on its own. And these type of discoveries are quite hard to come up if you're trying to optimize manually. So in terms of the whole algorithm, the part that we optimize, you can see in green and red, the part that we change and optimize, which is specifically between 8 and 16 bytes. And similar to sorting, our goal was really to try to push this and deploy this to an open source library so that other people could take advantage of this. In the case of hashing, it's particularly tricky because these are libraries that are used by many different coding applications and everyone has different constraints. And it's not like sorting where you can at least be sure that your function is correct, right? Here, what we were doing is that we start with an input distribution. We think we notice that our function is faster in our input distribution, but is it faster for everyone? We don't know, right? We are lucky that there is tools like Smashers that are tools built in order to test these functions. So they have many different type of inputs. So like we could try how resilient, how robust was our new hashing function. And also the Abseil library has some latency benchmark as well. So we did a lot of iteration here to find a very strong input distribution we would use for training. And then every time we change the input distribution, of course, AlphaDev would optimize the hashing function for that distribution. So there was a bit of iteration here, but then we came up with a good and robust hashing function that seemed to generalize very well. And we are happy to say that this hashing function has been accepted. So it's now part of Abseil, and it saves about 30% in latency compared to the previous one. Similarly to sorting, we conservatively estimated that it's called about trillions times per day. And as far as we are aware, it's the first time that reinforcement learning has been used to optimize this a hashing function, in a hashing algorithm in Abseil. And more important, we're happy to see that AlphaDev can generalize to domain ordered and sorting. So now that we saw sorting and hashing, it's good also to take a step back and see and ask the question, when can AlphaDev be impactful? What type of function can AlphaDev really optimize? And we come up with two properties. The property number one is either we can have exhaustive verification. So that is the case of sorting up to sort 8. Then it becomes a bit problematic, right? Because if we have to check all possible permutations, then it really doesn't scale. So here, a nice property for an algorithm is, can we check all possible inputs and guarantee that the algorithm is correct? If that's not possible, at least we need to be able to measure the quality. And that's the case of hashing, right? In hashing, we are not checking all possible permutations, but then we need to be able to measure to have a measure of quality. And this is for us is the number of collision. So either the first or the second are the properties that are really important. And we are lucky that there are quite a lot of algorithms that fall in these categories, right? From cryptographic hashing to serialization to lossless algorithms and so on. So, okay. So what other type, comparing to other works that has been around already. So in our paper, we do a bit of a better literature review, but very quickly here, there's been quite a lot of history, both in the program optimization and program synthesis, of course. And I would say that the main difference between our work and previous works is the fact that we optimize end-to-end for latency. So this is usually optimization has been done optimizing either for program length or maybe assigning a cost to each function, to each instruction. This is a little bit problematic because especially modern architectures, there is a lot of instruction parallelism. So it's very difficult. Optimizing directly for latency is a completely end-to-end approach. And of course, it's very challenging both because micro benchmarking can be very noisy, so we need to be very careful there. And the other challenge is that it's expensive, of course, right? So what really allowed us to get around is the fact that we had a model that estimates the latency, and then we would train this model as we discover new programs, right? So that's the nice trick that was able to make it work for us. So what are the limitations of our approach? Well, quite a few actually. So the first one is that we still don't support all algorithm structures like loops and recursions. So there is nothing that prevents us to add them. Actually, I think it's quite simple. Right now we support branching. So a loop in assembly is just a jump backwards. A branch is a jump forward. A loop, you basically jump to a previous label. It's just some engineering work. I think a few challenges here is that, for instance, when you measure latency, now it's very easy to create programs that never terminate. So maybe you need to time out things and things like that, right? We haven't prioritized that direction. Instead, a very interesting direction to me would be the SIMD instructions. So here is allow support for vectorized programs. I think that would be very impactful because it's quite challenging to write optimized SIMD operations. It's quite challenging for humans. I really would like computers to do that for us. So I think that would be a very impactful direction. And third, right now we optimize directly at the assembly level, which is very nice because we can find some nice optimizations. But then when we deploy these to open source libraries, we had to reverse engineer to C++. So maybe optimizing directly at the higher level languages would be preferable. It would make this tool easier to use. So where do we want to go from here? Where can we do? Well, when we looked at baselines, I mentioned how stochastic search is quite efficient, especially searching on the local space. So maybe there is a bit of scope to get the best of both worlds. So AlphaDev does very well in terms of coming up with novel and very different algorithms. And then we can do some stochastic search on those, right? Which is a lot more efficient, especially searching on the local space of a solution. So we use AlphaDev to come up with many different solutions, and then a little bit of stochastic search to search around the solution. So that's one direction, of course. The second one would be to combine language models with AlphaDev. So language models do very well in terms of coding. You see models that have been trained on all GitHub and all the code out there to be really good at like coming up with code, but they still miss a little bit of planning capabilities, right? Something I really would like these models to have is some RL on top of it. So what I really mean is a value function similar to how we have in AlphaDev, which is a value function that estimates the latency and correctness of the future actions. You could have something on top of language models like this, right? And this could be on top of, could be done at the token level, or could be done maybe at the sentence, or maybe at the snippet level, and so on, right? Value function that allows you to plan. And finally, the dream would really be to optimize both the software and hardware stack at the same time. And I really hope that one day we get there. So in conclusion, AlphaDev discovered faster sorting and hashing algorithms from scratch. We are very happy that both of them are now being deployed in C++ open source libraries, and they're being used trillions of times per day. I'm really happy also that this is like we show that reinforcement learning, that there is quite a lot of opportunity for reinforcement learning in this area. And it's also a nice win of reinforcement learning in an area that is not gaming related, but actually has impact in the real world. So this is the conclusion, the end of the talk for today. But of course, like feel free to reach out for any question, and more than happy to spend some time now to answer any question you might have.
Great. Oh yeah, I missed some stuff.
Great. Well, thank you so much. Yeah, so I see we have quite a few questions. Maybe we can just go through one by the order. We also just a reminder, everyone, if you have questions, please keep posting in the chat. And if you want to speak to ask questions, you can also raise your hand. I will unmute you. You can speak to ask questions.
So maybe we start going through, like, I think so the first one on performance counters is good question. So I might not sure if you know it, but like what we did is like we collaborated a bit with some like expert that were already doing some micron benchmarking within Google, and they gave us some suggestions in order to remove the noise. Like maybe something that I can try to find a good reasons why they didn't suggest CPU cycles if you want, and maybe reach out after. But it's a good question. I don't have a good answer to that. Sorry, I missed it.
Here we go.
Yeah, AlphaDev versus AlphaDev S versus okay, yes. So what are the main difference in architecture? So AlphaDev is the main agent that we have. So it uses like AlphaZero, uses a transformer, and so on. AlphaDev S is the stochastic search. So there is no learning component. So you don't have like a transformer. There is no latency value function. AlphaDev S, WS, and CS are the same agent. The only thing that changes is the CS stands for cold starting, so it starts from an empty buffer like AlphaDev, while WS stands for warm started, so it starts always from an already sorting programs. So it's just how we initialize those algorithms. But the architecture itself is very different, and the type of search they do is very different. AlphaDev does Monte Carlo tree search, while AlphaDev S does the stochastic search implemented by Stoke. That is the algorithm.
I think in terms of the next one, I guess taking a step back, in AlphaDev, we're going back to the reinforcement learning problem where we're trying to learn a policy that maximizes the rewards. And so the idea is that we're essentially doing solving the RL problem. So there are other optimization techniques out there that, you mentioned spiral optimization or stochastic optimization. I guess RL is a form of stochastic optimization. Yeah, our ultimate goal was to solve the Markov decision process by learning a policy that would maximize the expected rewards, or which were correctness and latency. So AlphaDev would win the game by learning a program that was both correct and fast. Okay.
So we have one raised hand. Let me give open his mic so he can ask questions. Give me 1 second.
Yeah. So yeah.
Okay, go ahead, Yush.
Hi. Yeah. So thanks Daniel and Andrea for the great talk, and thanks for the fundamental contribution to the field. So I have one question. As I understand, you optimize or search in the assembly space, but you convert it to the C++ space. So it is always possible, since you are thinking about optimizing all the computing stack. Also, it is related to interpretability. Yeah, thank you.
Yeah, I think this is a fantastic question. So there are a few reasons why she started with assembly. One, that we thought we could probably find some optimizations there more easily. And second, that assembly has some nice properties that fit very well in terms of RL, more properly, like in our case, every partial programs that you have in assembly can always be executed, and it gives you an output, which is intermediate registers and the state of the memory. So we feed that back to the algorithm. Like in C++, of course, if you execute like a partial program, that's probably going to be a program that doesn't compile and doesn't work, right? So there are some of these properties that fit very well in our setup. The good question that you ask is that, is it always possible to reverse engineer? So the answer is no. In our case, we were always able, but then there are some sometimes that we can discover some very esoteric things that it might not be so easy to reverse engineer. We worked very closely with a few people that are very expert in C++, and then they were able to always, and they almost as a game, always reverse engineer from any assembly to C++, but there are some stuff that you're dependent on the compiler, right? And so I think my gut feeling is that if we are able to optimize well directly on a higher level language, if our goal is to deploy to an open source library, we are not going to deploy assembly, right? So ideally, if the end goal is to have a higher level language, ideally we optimize at that level and we don't have the reverse engineering step.
Okay, great. Let's continue on the questions in the chat, and we will come back for the one if you raise the hand.
Let's see, if too many buckets.
I think, yeah, we had the one number of collisions. The one of collisions, it's a good question. So what we did also, we try to measure the impact that the hashing function not has in just measuring benchmarking it, but also as part of a much larger application. And with that internally, so we try to swap out this hashing function and we see oh, let's run this very long application and see measure if it has any impact on latency. And there we saw the savings, right? So I agree with you that there are it's not as simple as just minimizing the number of collisions. That's just the reward function that we optimized, and it seems to do well. There is probably scope for doing something a bit more clever than that. I think for some, we're also looking a bit at the entropy and different things, but
yeah, and I think regarding cache misses, I mean, one of the things is that the programs that we optimize, they're fairly long compared to what's been done in the past, but these are still small functions comparatively with respect to the cache. So cache misses will become more of an issue when you have really long functions that you're discovering, because then you won't be able to fit everything into the cache, and then you'll have these cache misses. But for the functions we were working with, that wasn't as much of an issue. And that's also probably why optimizing for minimizing collisions and latency worked well in the setup. Cool. Are you aware of review article in which GPUs? In terms of economic impact, I think it's a good question. I mean, taking a step back, the hope is that with the types of algorithms that are, if we optimize fundamental algorithms, these algorithms, will both hopefully save resources and therefore save money and have impact. And I think one of the key challenges is really identifying which of these fundamental algorithms we want to optimize. Because sometimes, it can be like, okay, let's optimize the sorting algorithm, which is how we started out, but we were like, well, which one? And it really took a lot of time for us to figure out that this particular sorting algorithm in this particular library made a lot of sense to try and optimize for. So I think, as a result of finding these fundamental functions, you can have realized economic and efficiency gains as a result, but it's really part of that discovery process, I think, to identify which ones can give you that.
For AlphaDev as an extension to the optimizer, I guess optimizer, you mean is the compiler optimization step? I assume so. In the case, it might be, I think the challenge is there, of course, is that it takes quite a bit of time to run AlphaDev. Well, if you compare your code, you want the compilation to be fast. The second is that right now, the way AlphaDev works is we have to define a reward function. So we need to decide how to optimize the program and run it. I think there is scope in the compiler for optimization, also for RL as well. So I think there are many layers of the compiler. So it would be really nice to have it.
I was also going to add, in terms of a compiler optimization, there is a work that we've just recently released, well, about 2 months ago. I've just shared it in the chat, which is called optimizing memory mapping using deep reinforcement learning. And here we use a variant of mu0 that we developed in order to optimize memory mapping. And that's if you're, for example, doing inference in a large machine learning model, you want to be able to take the tensors in that machine learning architecture and place them into fast memory in order to process it efficiently. But you can't put everything into fast memory because that's limited. And so it really learns the problem of mapping of when you put a tensor into slow memory versus when you put it into fast memory to improve inference time. So it's in the area of compiler optimization if you're interested, but that's definitely would be an exciting place to have impact.
Yeah, exactly. And I think it really changes the level at which you're operating. AlphaDev operates directly at the code level, while this paper that's done LinkedIn operates at a lower level, which I think would be more appropriate for the compiler.
Cool. There's a hand from Daniel Veroli.
Yes. Okay. So hey, Danny, I just unmute you. You should be able to please go ahead.
Yeah. Thank you so much. Thanks, Daniel and Andrea. This is really interesting. I had a question to you, Daniel, I guess. So you mentioned in the part that you were presenting so it seemed like for all the cases of the different sort, like sort 5 and sort 3 and the variable sorts, you went with the algorithm that had the least number of sequence or lines or operations, I guess. And in the case of sort 5, you said you didn't use the 42 one, you used the 43 one. I was just curious if I understood that correctly. Why was that the choice?
Yeah, it's a great question. It actually goes back to the previous question that was asked, where is it always possible to reverse engineer something to C++? And what we found is with the 42 instruction program, it was very difficult to reverse engineer to capture those gains. Whereas with the 43 instruction program that learned to apply the AlphaDev swap move 3 times, this was something that we could actually convert back to C++ and have the same gains as a result. So, but great question.
Okay, I see. Okay, great. Thank you so much.
Sure. Any plans to? Sorry. Where are we in the question?
Any plans to cross-source among data science to improve faster?
I think at this point, what we wanted to do, like the first goal we wanted to achieve was to discover improved fundamental algorithms that we could then, not just benefit from, but the entire community could benefit from. And so, these are now sort of out there with the sorting and hashing. I think it would be great for it to be turned into a tool. This isn't something that we're planning to do right now, but this is something. With the paper, we also released a lot of the code to regenerate these networks. And so this is something we're hoping we can also get help from the open source community to do, because I think that there's many other fundamental functions out there that can be optimized. And so having a general purpose tool and hopefully using our code to do so, and feel free to reach out to us if you have questions, etc., would be great. I think there was one more.
Yeah, the libc++.
What is the version of libc++ these changes got merged? Well, we
You
can
can find the commit, right?
Yeah, I'll share with you now the commits.
Yeah.
Where is it? So here we go. Okay, so yeah, I've just shared it in the chat. So yeah, hopefully that has got the answer to your question. And then, oh, there's one more question here. Have you considered using open source CPU cores where you can measure precisely the number of clock cycles spent on micro ops as opposed to macro assembly instructions where the number of assembly instructions does not correlate with the number of clock cycles? So I would say here, I think the question is whether we can get a way of measuring this in a noise-free way. So one of the things that was really important in our setup was to create an environment that was as noise-free as possible. And I think if we can do that here, and if you think that there's a way in which this can be noise-free enough to optimize for this latency, then yeah, this in principle we should be able to do that. But yeah, feel free to send us any information you have, and we can look into it as well.
I think we have a last question.
So maybe. Oh, RL in compiler optimizer, is that the one?
Yeah.
Okay. Once one gets a program working, if it's a long batch program might be without the optimizer run overnight. Yeah, that might be the case. I'm not sure I fully understand the question, but yeah, feel free to reach out to us to maybe just give a bit more context would be helpful.
David, if you want to raise your hand, I can unmute you to ask questions. We have one question, raise hand, Seth, go ahead, please. You can speak to our question.
Awesome. Thank you. Hey, how's it going? My name is Caesar. Thank you so much for the information. Honestly, I wanted to know if you guys are planning on doing a workshop, kind of setting one of these up, an algorithm optimizer. I'm not sure if there is already one that you guys have, but it's interesting. I'm new to the AI community, so I just kind of wanted to get some info.
Yeah, it's a great idea. I know that there are like the specific libraries sometimes have algorithm optimization workshops. I think LLVM has one. I would suggest this isn't sort of on our map yet, sort of on our roadmap as yet, but it's definitely something we should think about. But also, if you search for LLVM optimization workshops, I think you should find quite a few different options there, because I think they have annual workshops that they run every year.
All right, I think we cover all the questions. And for those one, if we didn't got your question answered, you can post the questions later to we unfortunately run out of time. And yeah, thanks Daniel and Andrew for the presentation and Q&A with our attendees. Do you guys have any like last minute anything to want to add on before we end the day?
I mean, just thanks so much for having us. It was great to engage with the community. Feel free to reach out if you have questions. And yeah, we hope that you can also take inspiration from the technology and some of the areas we think you can have further impact in. And it'd be great to kind of see more use cases of RL improving program optimization.